Look up at the night sky, and you'll see more than just stars. You'll witness a grand, silent dance of patterns, so precise they feel almost intentional. Take the spirals of galaxies, for instance. Their sweeping arms don't twist randomly. They follow the same mathematical rhythm found in seashells, hurricanes, even the way leaves unfurl. This is the Fibonacci sequence, a hidden code woven into the fabric of reality itself. But here's the chilling question: what if this isn't just a coincidence? What if these symmetries are clues, whispering that the universe operates by rules far deeper and more elegant than we've ever imagined? That's the mystery we're diving into today. Across cultures and centuries, humans have sensed there's something uncanny about the way nature repeats its designs, from the branching of trees to the orbits of planets. It's as if the cosmos is obsessed with balance, echoing the same shapes and ratios at every scale. And scientists are now uncovering evidence that these patterns might not be accidental. They could be signatures of a fundamental symmetry, a hidden architecture stitching space, time, and even the laws of physics into a unified whole. Imagine discovering that everything from the tiniest quark to the vastest supercluster is playing by the same invisible rulebook. That's where these 30 theories come in. Some will sound like science fiction, dimensions folded like origami, particles acting as mirrors to parallel universes, even the idea that black holes might be cosmic symmetry enforcers. Others will feel eerily familiar, like déjà vu for the soul, echoes of ancient philosophies now backed by equations, but all of them point to one electrifying possibility: the universe isn't just built on chaos. It's built on harmony. So if you've ever stared at the stars and felt like they were speaking in a language just beyond your grasp, stick around. By the end of this journey, you might finally start to understand it. Ever wondered if there's a mirror version of reality we just can't see? That's the tantalizing idea behind supersymmetry, or SUSY for short, one of the most elegant theories in modern physics. Picture this: every particle we know, from the humble electron to the elusive neutrino, has a hidden twin. These superpartners would be like cosmic shadows, identical in every way except one: their mass. And here's where it gets wild. If these twins exist, they could solve one of the universe's biggest puzzles: dark matter. Right now, when we peek at galaxies, we see stars orbiting way too fast for the visible matter to hold them together. Something invisible, something massive, must be gluing them in place. Enter SUSY stealthy superpartners. The lightest of these twins wouldn't interact with light, making them ghostly perfect candidates for dark matter. But SUSY ambition doesn't stop there. It dreams of stitching together nature's fundamental forces: gravity, electromagnetism, and the nuclear forces into a single, seamless tapestry. Think of it like finding out electricity and magnetism were secretly two sides of the same coin. SUSY suggests all forces were once united in the early universe's unimaginable heat, before symmetry broke like a cosmic mirror shattering. So where's the proof? That's where the Large Hadron Collider comes in. This 17-mile underground ring smashes particles at nearly light speed, recreating conditions a fraction of a second after the Big Bang. Scientists hoped SUSY particles would show up in the debris, but so far the collider's detectors have stayed quiet. Some argue this silence means SUSY is dead, while others whisper we just haven't probed deeply enough. The hunt continues, because if SUSY is real, it wouldn't just rewrite physics textbooks, it'd reveal a universe where every speck of dust, every beam of light, has a hidden twin waiting to be found. But what if the universe's symmetry isn't just hidden in particles? What if it's folded into the very shape of space itself? That's where string theory throws open the doors to a reality far stranger than we ever imagined. Picture this: all those fundamental particles we've been studying, they might not be dots at all. Instead, they could be tiny, vibrating strings, each oscillation producing a different note in the cosmic symphony. But here's the twist: for the math to work, these strings need room to dance. not just the 3 dimensions we know or even 4 with time. Try 10 or maybe even 26. Now, before your brain rebels at the idea of all those extra dimensions, think of an ant crawling along a telephone wire. From a distance, the wire looks like a simple one-dimensional line. But zoom in close enough, and the ant reveals a secret. The wire has thickness, a hidden dimension wrapped so tightly it's invisible to the naked eye. That's how string theory imagines our reality. The extra dimensions aren't missing, they're coiled up smaller than an atom, like microscopic origami tucked into the fabric of spacetime. And here's where symmetry sneaks back in. Those curled-up dimensions aren't random, they're sculpted by precise mathematical shapes called Calabi-Yau manifolds. These forms are so exquisitely balanced that they could explain why particles mirror each other, why forces unify at high energies, even why the universe leans toward elegance rather than chaos. It's as if the cosmos is a grand cathedral, and these hidden dimensions are its vaulted arches, invisible from the outside, but holding everything together with perfect geometry. So why can't we see them? Imagine blowing up a balloon with dots on its surface. To a flat, two-dimensional creature living on that balloon, those dots just move apart as it inflates. But we, in 3D, see the truth. The dots are separating because the balloon itself is expanding. Similarly, our perception might be trapped in a slice of reality too narrow to sense the full symphony of dimensions. Yet if string theory is right, every particle collision, every gravitational ripple, might carry echoes of those folded symmetries like whispers from a hidden room in the fabric of the universe. The catch proving it, unlike Sussy, string theory doesn't yet have a smoking gun prediction we can test in a lab. Some argue it's more philosophy than physics, while others believe we're simply waiting for a breakthrough, a cosmic Rosetta Stone to decode dimensions we can't yet measure. But whether it's right or wrong, string theory has already gifted us something profound, a vision of reality where symmetry isn't just a curiosity, it's the scaffolding of existence itself. Now imagine if everything you see, every star, every galaxy, even your own hands, wasn't truly three-dimensional at all. What if it was all just an illusion, a shimmering projection from a hidden two-dimensional surface at the edge of the universe? This isn't science fiction. It's the holographic principle, one of the most mind-bending ideas in modern physics, and it might just hold the key to understanding the universe's deepest symmetries. The story starts with black holes, those cosmic vacuum cleaners that swallow everything, even light. In the 1970s, physicist Leonard Susskind stumbled onto a paradox. If you toss an encyclopedia into a black hole, where does all that information go? According to Einstein's general relativity, it's gone forever, crushed into the singularity. But quantum mechanics insists information can't just vanish, it has to be preserved somehow. Susskind's breakthrough was realizing the information isn't lost. Instead, it gets smeared across the black hole's event horizon, the point of no return, like invisible ink on a cosmic ledger. Here's where it gets wild. The surface area of that horizon, a flat two-dimensional membrane, seems to encode everything that happens inside the black hole's three-dimensional volume. It's as if the 3D interior is just a holographic projection of data written on a 2D surface. And if that's true for black holes, why not for the entire universe? The holographic principle suggests our reality might work the same way, that every particle, every force, every event in our 3D world is actually information painted on a distant two-dimensional boundary we can't perceive. Think of it like watching a movie. The screen is flat, just a grid of pixels, yet it creates the illusion of depth, movement, even emotion. The holographic universe theory argues we're living inside that illusion. The math even checks out. The amount of information in any region of space doesn't scale with its volume, as you'd expect, but with its surface area. It's as if the universe is fundamentally two-dimensional, and the third dimension is just a convenient trick, a cosmic sleight of hand. But how could this possibly solve symmetry puzzles? If the holographic principle is true, then symmetries we observe, like the way particles mirror each other or forces unify, might not be features of our 3D world at all. They could be shadows of simpler, more elegant symmetries playing out on that distant 2D boundary. It's like realizing the intricate patterns in a kaleidoscope aren't coming from the glass itself, but from the way light bounces off mirrors hidden in the base. Of course, this raises questions we can barely grasp. Where is this boundary? How does the projection work? And if we're just holograms, what or who is holding the projector? For now, these mysteries linger at the edge of science, where mathematics brushes against philosophy. But the holographic principle has already reshaped how we see reality. It suggests that the universe's deepest symmetries might not live in the world we experience, but in a hidden, lower-dimensional canvas we're only beginning to decode. What if the universe's hidden symmetry wasn't just elegant, but breathtakingly beautiful? That's the radical vision of physicist Garrett Lissy, who dared to propose that all particles and forces might fit together like jewels in an 8-dimensional snowflake called the E8 Lie group. Picture the most intricate kaleidoscope imaginable, a geometric pattern with 248 perfectly balanced points, each representing a possible particle or interaction. Now imagine that this isn't just art, but the actual scaffolding of reality itself. Lissy's theory starts with a mathematical object so symmetrical that mathematicians once called it the most beautiful structure in existence. The E8 group is like a cosmic chandelier, every facet reflecting and connecting to the others with perfect harmony. In this model, familiar particles like electrons and quarks aren't random accidents. They're notes in an 8-dimensional symphony, their properties determined by how they sit within this grand geometric lattice. Even gravity, which stubbornly resists unification with other forces in traditional theories, finds its natural place here as just another facet of the pattern. Visualizing E8 is like trying to hold the blueprint of a cathedral in your mind, only this cathedral exists in a space with 8 times the dimensions we experience. Scientists use intricate projections to flatten slices of it into 3D animations, revealing mesmerizing structures that resemble fractal flowers or the branching veins of a leaf. These aren't just pretty pictures, each twist and intersection corresponds to how particles might transform into one another, suggesting a universe where matter and energy dance to an unseen geometric rhythm. But why 8 dimensions? Think of it like this: when you play a note on a piano, the sound seems simple, but hidden within it are harmonics, higher frequencies vibrating in perfect mathematical ratios. The E8 group suggests our familiar 4-dimensional spacetime might just be the fundamental note, with 4 extra dimensions humming silently beneath the surface, orchestrating the universe's symmetries in ways we're only beginning to hear. Not everyone's convinced. Critics point out that Lissy's model makes few testable predictions, and some physicists argue it's more poetry than particle physics. Yet even skeptics admit there's something haunting about how neatly known particles slot into E8's architecture, like finding out your childhood doodles accidentally solved advanced calculus. Whether it's the final theory or just a stepping stone, E8 reminds us that the universe might not just follow mathematical rules. It might be mathematics crystallized into breathtaking form. And here's the most tantalizing part: if E8 truly describes nature's symmetry, then every interaction in the cosmos, from the spin of an electron to the whirl of galaxies, is just the universe tracing the edges of this invisible masterpiece. We're not just studying physics anymore, we're watching geometry come alive. What if the Big Bang wasn't the beginning, just the latest page in an infinite cosmic story? That's the mind-stretching premise of conformal cyclic cosmology, a theory by Nobel laureate Roger Penrose that imagines universes reborn in an endless loop of death and renewal. Here's how it works. When our universe reaches heat death, a state where all energy is evenly spread and nothing can happen anymore, something miraculous occurs. The vast, cold emptiness gets stretched and rescaled like a cosmic rubber band until it's mathematically indistinguishable from the searing hot singularity of a new Big Bang. The end becomes the beginning, symmetrically, forever. Penrose calls this process conformal rescaling, a geometric transformation where distances and times are stretched, but angles and shapes remain perfectly preserved. Imagine taking a photograph of the universe at its final moment and shrinking it down to a single point. All the information is still there, just rewritten in a new cosmic language. The equations suggest that under this transformation, the infinite future of one universe seamlessly stitches onto the infinite past of the next, creating a chain of universes with no true start or end. But how could we ever prove something so audacious? Penrose points to eerie patterns in the cosmic microwave background, the afterglow of the Big Bang. These are concentric rings of slightly warmer or cooler spots, which he calls Hawking points, named after his late colleague Stephen Hawking. According to the theory, these rings are imprints from collisions of supermassive black holes in the previous universe, their gravitational waves echoing across the cosmic reset like fingerprints on a reborn world. It's as if the universe is leaving breadcrumbs for us, subtle, symmetrical signatures of its cyclical nature. Skeptics argue these patterns could be statistical flukes, and the math behind conformal rescaling remains controversial. But if Penrose is right, the implications are staggering. Time itself would lose its arrow, with each cycle's end birthing a new beginning in perfect symmetry. The laws of physics might evolve slightly each round, explaining why our universe seems fine-tuned for life. And somewhere out there, in the ashes of a long-dead cosmos, another version of you might be staring up at the same stars, wondering if the universe remembers its past. The most poetic part, this theory doesn't just connect universes, it connects ideas. It blends the vast scales of general relativity with the quantum weirdness of black hole physics, suggesting that the universe's deepest symmetries might not be in space or time, but in the way existence itself can fold, reset, and begin anew. Whether Penrose's vision holds or not, it reminds us that the cosmos might not just be symmetrical in its laws, but in its very heartbeat. What if the key to unifying gravity and quantum mechanics was hiding in plain sight, not in our universe but in its shadow? That's the startling promise of the AD/CFT correspondence, a theoretical bridge between two seemingly unrelated worlds. On one side, you have anti-de Sitter space, a bizarre, negatively curved universe where gravity behaves like a cosmic trampoline, pulling objects toward its edges. On the other, a quantum field theory living on that universe's boundary where particles dance without gravity at all. The revelation, these are mirror images of the same physics written in different languages. Take a black hole in anti-de Sitter space. According to Einstein, its immense gravity warps spacetime into a singularity. But the AD/CFT duality suggests something extraordinary. All the information about that black hole, its mass, its temperature, even the quantum states of matter it swallowed, is perfectly encoded on the universe's distant boundary where gravity doesn't exist. It's like watching a 3D movie and realizing the entire story was secretly embedded in the flat barcode on your ticket. This holographic sleight of hand resolves one of physics' most vexing puzzles: how black holes can simultaneously obey Einstein's gravity and quantum mechanics' strict no-deleted data rule. Here's where it gets even stranger. The thermal radiation Hawking predicted black holes emit, on the boundary, it's just ordinary heat in a quantum system, no event horizons required. The math shows these two descriptions are computationally identical, as if the universe ran the same program on different hardware. Physicists call this gauge-gravity duality, and it's more than a neat trick. It suggests that spacetime itself might emerge from quantum entanglement like a 3D mirage rising from a 2D desert. But why anti-de Sitter space? Our universe is expanding, not curving inward. Think of it as training wheels for theorists. Add S's negative curvature creates natural walls, making calculations manageable. The real test will be extending this symmetry to our cosmos. Some hint at clues in the cosmic microwave background, where quantum fluctuations from the Big Bang's boundary might have seeded galaxy clusters. Others whisper that even our reality could be a hologram, its deepest truths painted on some unimaginable edge we've yet to find. What makes add S/CFT revolutionary isn't just its mathematical beauty, it's the way it forces us to rethink where physics lives. If a black hole's fiery heart is truly mirrored in a gravity-free quantum system, then the universe's symmetries aren't just hidden in particles or dimensions. They're woven into the very nature of reality, suggesting that the deepest laws might not reside in the world we see, but in the shadows it casts. Ever stumbled upon a number system so strange that even mathematicians call it the crazy uncle in the attic? Meet octonions, an 8-dimensional mathematical oddity where basic arithmetic rules like 2 times 3 equals 3 times 2 suddenly break down. At first glance, they seem like pure abstract playthings, the kind of thing only a theoretician could love. But dig deeper, and you'll find octonions whispering tantalizing secrets about the universe's hidden wiring, especially when it comes to the messy quantum world of quarks and gluons. Take quark colors. No, they're not actual colors, it's just physicists being playful with language. Quarks come in 3 flavors: up, down, strange, etc. But each flavor also carries one of 3 color charges: red, green, or blue. These colors aren't just labels, they dictate how quarks stick together via the strong nuclear force mediated by gluons. The math behind this, a symmetry group called SU3, which describes how colors mix and swap like ingredients in a cosmic smoothie. Now here's the kicker. The structure of SU3 fits snugly inside octonion geometry, like a key slipping into a lock. It's as if nature built quarks using pieces of an 8-dimensional puzzle we're only now assembling. But octonions aren't just handy for quark colors, they might be the missing link in unifying physics. The standard model's forces, electromagnetism, weak and strong nuclear, all arise from symmetry groups tied to specific numbers. Electromagnetism works with complex numbers 2 dimensions, the weak force needs quaternions 4 dimensions, and the strong force, as we just saw, it vibes with octonions 8-dimensional strangeness. This progression 2, 4, 8 isn't random. It mirrors the Cayley-Dickson construction, a mathematical ladder that builds each new number system by doubling the dimensions of the last. Could the universe be climbing this same ladder, using octonions to sew together its forces? There's a catch, though. Octonions are non-associative, meaning if you multiply 3 numbers, the order matters. A times b times c isn't the same as a times the quantity b times c. This makes them notoriously slippery to work with, but also eerily suited to quantum uncertainty, where particles don't play by classical rules. Some theorists, like physicist Cole Fury, have shown that octonions can elegantly generate the standard model's particle spectrum, with quirks like electric charge quantization emerging naturally from the math. It's like discovering that a bizarre set of musical notes automatically composes every known melody in existence. Yet for all their promise, octonions remain controversial. Critics argue they're too unstable to describe reality, like building a skyscraper on Jell-O. Others counter that their weirdness might be exactly what we need to crack open quantum gravity. After all, if spacetime itself emerges from quantum entanglement, who's to say its deepest rules follow ordinary logic? Maybe the universe's blueprint was written in octonions all along, a cryptic, 8-dimensional code waiting for us to decipher its symmetrical heart. So next time you hear that 2 plus 2 equals 4, remember, down in the quantum depths, the numbers might be dancing to a far stranger rhythm. One where multiplication tables twist like Möbius strips, and the universe's secrets hide in dimensions we can't even multiply properly. Picture a universe where every particle is swapped with its mirror image. its electric charge flipped and time itself running backward. At first glance, it sounds like science fiction, but this bizarre transformation is at the heart of one of physics' most sacred principles, CPT symmetry. The idea is disarmingly simple. If you take any physical process and simultaneously reverse charge c, parity p, and time t, the laws of physics should behave exactly the same. Electrons become positrons, left becomes right, cause and effect flip places, and yet the cosmic ledger stays perfectly balanced. This symmetry isn't just mathematical elegance, it's woven into the fabric of quantum field theory itself. Every equation we use to describe particles respects CPT as an unshakable rule, but here's where the mystery deepens. While the universe seems to adore this trifecta of reversals, it gets squeamish when we try them one at a time. Take antimatter, for instance. If you only flip charge turning matter into antimatter, nature flinches. Antimatter behaves slightly differently, which is why our universe isn't just empty radiation from matter-antimatter annihilation. Similarly, parity symmetry alone fails spectacularly in weak nuclear interactions, where certain particles only spin left-handed, and time reversal. Quantum measurements like collapsing a wave function seem to carve an arrow into time that can't be undone. Yet when you combine all three, charge, parity, and time, the universe suddenly relaxes into perfect harmony. It's as if reality has a secret handshake: break one symmetry and the others compensate like cosmic acrobats. This delicate dance might hold clues to why we exist at all. During the Big Bang, matter and antimatter should have been created in equal amounts, cancelling each other out in a flash of gamma rays. The fact that we're here means something. Some subtle asymmetry must have tipped the scales. CPT insists this can't happen in isolation, but perhaps tiny violations in individual symmetries added up like microscopic cracks in a diamond. Experimentalists have spent decades hunting for even the faintest whiff of CPT violation. They've compared the magnetic moments of protons and antiprotons with mind-bending precision, 10 decimal places and counting. They've trapped antihydrogen atoms, watching their spectral lines for any deviation from regular hydrogen. So far, CPT symmetry stands unbroken, but the search continues in particle colliders and atomic clocks. If we ever find a crack in this mirror, it could shake physics to its core, revealing hidden layers of reality where our symmetries are just approximations of something deeper. What makes CPT so profound isn't just its resilience, it's how deeply it's tied to the nature of spacetime itself. Some theories suggest that CPT symmetry might be the reason spacetime has 4 dimensions, 3 of space, 1 of time. Others speculate it could be a shadow of higher dimensional physics, like a hologram projecting from the edge of the universe. And then there's the wildest idea of all, that CPT symmetry isn't just a property of our universe, it's the reason our universe exists. If the Big Bang was a perfectly symmetrical event, perhaps CPT is the cosmic glue that kept it from collapsing back into nothingness. For now, CPT remains both a cornerstone and a conundrum, a symmetry so perfect we've never seen it break, yet so enigmatic it might hold the keys to existence itself. Whether it's the final word or just a signpost to deeper truths, one thing's certain: the universe seems obsessed with balance, even when it's hiding its most explosive secrets behind a veil of flawless symmetry. Imagine zooming into the fabric of reality, from the vast swirl of galaxies down to the frantic dance of quarks, and finding the same rules at every level. That's the dream of scale symmetry, the idea that physics doesn't care about size. No matter how far you zoom in or out, the equations stay the same, like a cosmic fractal where patterns repeat infinitely. But reality, it turns out, isn't quite so tidy. Take fractals, those mesmerizing shapes where every tiny piece mirrors the whole. A fern's leaf looks like a smaller version of the branch, which looks like the whole plant. Some theorists wonder, could the universe work the same way? There are hints. Galaxy clusters resemble neuron networks in the human brain. turbulent fluids twist in patterns eerily similar to interstellar gas clouds. Even the distribution of matter in the cosmos follows a fractal-like hierarchy, clusters within clusters, all the way down. It's as if nature has a favorite blueprint it can't stop reusing. But here's the catch. While the universe looks fractal at certain scales, the forces governing it don't play fair. Gravity dominates galaxies but vanishes inside atoms. The nuclear force that glues protons together is powerless across a grain of sand. This symmetry breaking frustrates physicists dreaming of a unified theory. Why should the rules change just because we're looking at a different zoom level? Some suspect hidden layers of reality might restore the balance. In string theory, vibrating filaments could blur the line between quantum and cosmic scales. Others propose scale-invariant modifications to gravity, where the force weakens or strengthens to match observations at any size. Then there's the controversial fractal universe hypothesis, suggesting space-time itself has a fractional dimension. Not quite 3D, not quite 4D, but something in between, smoothing out the discrepancies. Critics, though, point to cold, hard data. Particle colliders show quantum realms where symmetries shatter unpredictably. Cosmic microwave measurements reveal a universe statistically smoother than any fractal model predicts. Yet even skeptics admit the appearance of scale symmetry is haunting. Maybe it's a shadow of deeper physics, a relic from the Big Bang when all forces truly were one. Or perhaps, as with so many of the universe's secrets, we're still just scratching the surface of the pattern. Right after the Big Bang, the universe should have been a perfect balance of matter and antimatter, equal parts creation and annihilation, leaving behind nothing but pure energy. Yet here we are, in a cosmos overflowing with galaxies, stars, and planets made entirely of matter. So where did all the antimatter go? This is the baryon asymmetry problem, one of physics' most baffling mysteries, and it hints that the universe's cherished symmetries might have a hidden bias. The puzzle starts with a simple observation. Every particle we know has an antimatter twin with opposite charge. Electrons have positrons, protons have antiprotons, even neutrinos have antineutrinos. When matter and antimatter meet, they obliterate each other in a flash of gamma rays. Based on this, cosmologists expected the early universe's explosive energy to produce equal amounts of both. But somehow, for every billion antimatter particles, there were 1,000,000,001 matter particles, a tiny asymmetry that snowballed into everything we see today. Enter physicist Andrei Sakharov, who in 1967 laid out 3 conditions needed to tilt the cosmic scales. First, the universe had to violate baryon number conservation, meaning processes could create more matter than antimatter. Second, there had to be both C charge and CP charge parity symmetry violations to break the perfect mirror between particles and antiparticles. And third, all this had to happen out of thermal equilibrium, a chaotic, unstable environment where symmetry-breaking fluctuations could stick. For decades, these conditions seemed impossible to meet. Then experiments revealed the first cracks in the mirror. In 1964, researchers found that certain particles called kaons decay slightly differently than their antimatter counterparts, a direct CP violation. More recently, studies of B mesons at particle colliders confirmed the effect, showing antimatter doesn't quite play by the same rules. But these deviations are vanishingly small, far too feeble to explain the universe's overwhelming matter surplus. That's where neutrinos enter the story. These ghostly particles, which barely interact with matter, might be smuggling the answer. If neutrinos are their own antiparticles, a phenomenon called Majorana particles, they could have triggered a process called leptogenesis in the early universe. Here's how it might work. Ultra-heavy neutrinos from the Big Bang decayed asymmetrically, producing more matter than antimatter. Then, through quantum quirks, that imbalance transferred to quarks, seeding the matter-dominated cosmos we inhabit. Experiments like Japan's Super Kamiok and the upcoming Deep Underground Neutrino experiment are hunting for signs of this. They're watching for neutrino-less double beta decay, a rare atomic process that would prove neutrinos are Majorana particles. Others are measuring neutrino oscillations with unprecedented precision, seeking subtle CP violations in how neutrinos morph between flavors. If either finds a smoking gun, it could reveal how a universe built on symmetry ended up so lopsided. The stakes couldn't be higher. Solve the baryon asymmetry problem, and you don't just explain why we exist, you uncover physics beyond the standard model, perhaps even clues to quantum gravity. It's a reminder that symmetry, for all its beauty, might be the universe's starting point, not its final word, and that the most profound secrets could be hidden in the faintest imbalances, written in the afterglow of creation itself. Einstein called it spooky action at a distance, the bizarre phenomenon where two quantum particles become entangled, and changing one instantly affects its partner, no matter how far apart they are. This quantum entanglement defies our everyday intuition about space and causality, suggesting some invisible thread connects particles across the cosmos. But what if that thread isn't just a metaphor? What if entanglement is actually a clue pointing to a hidden symmetry woven into spacetime itself? Enter the ER=EPR conjecture, a radical idea that links two of physics' most mind-bending concepts. On one side, you have Einstein-Rosen bridges, better known as wormholes, hypothetical tunnels through spacetime that could connect distant points in an instant. On the other, EPR pairs entangled particles named after Einstein, Podolsky, and Rosen, who first grappled with their strange behavior. The conjecture suggests these aren't separate phenomena at all. Entanglement might be creating microscopic wormholes, stitching the universe together with an invisible network of quantum shortcuts. Picture two black holes connected by a wormhole. According to general relativity, anything falling into one would emerge from the other, preserving the information but scrambling it beyond recognition. Now imagine those black holes are quantum particles. The wormhole becomes the entanglement itself, a geometrical bridge ensuring that whatever happens to one particle immediately reflects in its partner, no matter the distance. It's as if the universe cheats by folding spacetime to maintain perfect symmetry between them. This idea turns entanglement from a mathematical oddity into something tangible, a physical structure in spacetime. Normally, we think of empty space as just empty, but if ER=EPR is right, the vacuum might be teeming with these tiny wormholes, their mouths opening onto entangled particles scattered across the cosmos. The fabric of reality could be less like a smooth sheet and more like a cosmic lace, threaded with connections we're only beginning to map. The implications are staggering. If entanglement really does create spacetime geometry, then the symmetries we observe in quantum mechanics might be shadows of deeper gravitational truths. It could explain why black holes preserve information. Their interiors might be linked to external particles through these wormholes. Even the holographic principle fits neatly into this picture, with entangled qubits on a boundary encoding the wormhole's interior like a cosmic QR code. Of course, the math is far from settled. Wormholes in general relativity require exotic matter with negative energy to stay open, something we've never observed. And while quantum entanglement is experimentally proven, no one's glimpsed a wormhole in the lab yet, but physicists are exploring ways to test the idea. Some propose looking for signatures in the quantum noise of entangled systems, where wormhole-like correlations might appear. Others suggest tabletop experiments with ultra-cold atoms, where entangled states could mimic wormhole dynamics under carefully controlled conditions. Whether ER=EPR holds up or not, it's already reshaped how we see reality. Entanglement isn't just a quirk, it might be the universe's way of keeping its books balanced, ensuring that no particle ever truly acts alone. And if that's true, then every time we measure a quantum particle here, we're not just observing a tiny piece of the cosmos, we're tugging on threads that might weave through dimensions we can't even see. Ever run your finger across a quartz crystal and marvel at its perfectly repeating pattern? Now imagine the fabric of reality itself might be built the same way, not smooth, but an intricate lattice of space-time, pixels at the smallest scale possible. This is the startling vision of crystallographic universe theory, where existence isn't continuous but stitched together from Planck-sized building blocks arranged in flawless symmetry. At the heart of this idea is the Planck length, about 1.6 times 10 to the negative 35th meters. That's so small, if you blew up an atom to the size of our solar system, the Planck length would still be tinier than a single tree on Earth. Quantum physics suggests that below this scale, space-time loses all meaning. It's not just that we can't measure it, the very concepts of before and after, here and there, dissolve into quantum foam. But what if that foam isn't random? What if it's structured like a cosmic diamond, with every atom of space-time locked into an immutable geometric pattern? Think of how quartz crystals form. Their silicon and oxygen atoms don't just clump together, they arrange in repeating tetrahedrons, creating symmetries so precise they can bend light in predictable ways. Crystallographic universe theory proposes space-time does something similar at the Planck scale, with its fundamental units snapping together like pieces of an unimaginably complex puzzle. Mathematical models suggest these units could form hyperdimensional shapes, not just cubes or pyramids, but exotic configurations with names like E8 lattices or Leech lattices, each with symmetries that make quantum interactions click into place like gears in a watch. This isn't just poetic speculation. If space-time is crystalline, it could solve some of physics' thorniest problems. Take black hole entropy, the mysterious way these cosmic vacuum cleaners seem to encode information on their surfaces. In a crystallized universe, the event horizon might literally be a fault line in spacetime's lattice, where Planck scale pixels rearrange to store data, much like defects in a crystal store energy. Even quantum weirdness like entanglement could get a geometric explanation. Particles separated by light years might still be neighbors in the lattice's higher dimensional structure, connected through folds we can't perceive. But how would we ever detect such a tiny architecture? Some theorists look to gamma-ray bursts, the universe's most violent explosions. If spacetime is discrete, ultra-high-energy photons from these bursts might interact with the lattice as they cross billions of light-years, subtly slowing down based on their wavelength. Others proposed tabletop experiments with supercooled atoms, where quantum vibrations could reveal hints of spacetime's underlying graininess, like feeling sandpaper's grit through a glove. Of course, skeptics argue this veers into untestable metaphysics. After all, the Planck scale is a quadrillion times smaller than anything we've probed. Yet history shows that when symmetries appear in nature, from snowflakes to galactic spirals, they're usually signposts to deeper truths. Whether spacetime is truly a crystal or not, the idea reminds us that the universe might not just follow mathematical rules. It might be mathematics frozen into physical form at the very foundations of reality. And if that's true, then every star, every atom, even the empty space between them, is just the glittering surface of a hidden symmetry too perfect to see, but not too perfect to imagine. Back in 1867, physicist James Clerk Maxwell proposed a thought experiment that seemed to break the laws of thermodynamics. A tiny, intelligent being that could sort fast-moving molecules from slow ones, creating energy from nothing. He called it a demon, and for over a century, scientists wrestled with how this creature could defy entropy. Today, we know the answer lies not in physics alone, but in the hidden symmetry between information and energy, a revelation that's reshaping our understanding of reality itself. Picture Maxwell's demon perched between two chambers of gas, opening and closing a trapdoor to let only speedy molecules pass one way. Over time, one side grows hotter, the other colder, energy seemingly conjured from thin air. The catch: the demon isn't just moving molecules, it's tracking them. every measurement, every decision to flip the door requires gathering and storing information. And here's the twist. In 1961, Rolf Landauer proved that erasing information always generates heat. That tiny puff of entropy balances the books, preserving the second law. Information isn't just data, it's a physical thing as real as a piston or a steam engine. This connection runs deeper. Landauer's principle suggests that information has mass, a mind-bending idea that ties back to Einstein's E equals mc squared. Flip a bit in a computer from 0 to 1. You're not just changing a symbol, you're tweaking the energy state of electrons and thus their gravitational pull. In theory, a perfect, lossless computer could run forever without heating up because it wouldn't erase anything. It'd just shuffle information in flawless symmetry, like a cosmic abacus balancing itself. Now scale this up to black holes. When matter falls in, its information isn't destroyed, it's scrambled onto the event horizon's surface, pixelated at the Planck scale. This holographic principle mirrors Maxwell's Demon's ledger. What looks like chaos from one angle is pristine order from another. Even quantum entanglement plays along. Two particles linked across space might be sharing information through some deeper, symmetrical structure we've yet to map. The lesson: the universe seems obsessed with keeping its books balanced, whether through heat, gravity, or quantum spin. Maxwell's demon wasn't breaking physics, it was hinting at a truth we're only now grasping. That information isn't just in the universe. It might be what the universe is made of. Deep in the abstract wilderness of mathematics, there exists a structure so vast and intricate that even seasoned mathematicians call it the monster, not for its ferocity, but for its staggering complexity. This is the monster group, a symmetrical behemoth with more elements than there are atoms in 1,000 Milky Way galaxies. Picture a Rubik's Cube, but instead of 6 faces with 9 squares each, imagine a puzzle with 10 to the 53 possible configurations, a number so large it dwarfs the age of the universe measured in Planck times. Yet this isn't just a numerical curiosity. The monster might hold the key to bridging two seemingly unrelated worlds, pure mathematics and quantum gravity. The story begins in the 1970s when mathematicians stumbled upon an eerie pattern while classifying symmetry groups, the abstract frameworks that describe how objects can rotate, reflect, or transform without changing their essence. Most groups fit into tidy families, but a handful resisted categorization, with the monster reigning as the largest and most elusive sporadic group. For decades, it seemed like an isolated oddity until a physicist named John Mackay noticed something uncanny in 1978. While doodling the monster's properties, he spotted the number 196,883 popping up, a figure that also appeared in a seemingly unrelated area of math called modular functions, which describe the twisting of donut-shaped spaces in string theory. This bizarre coincidence sparked monstrous moonshine, a term coined because the connection seemed so far-fetched it felt like mathematical moonshine, wild speculation with no rigorous proof. But the joke turned profound when mathematicians Richard Borcherds proved in 1992 that the link was real. The monster group symmetries weren't just coincidentally aligned with modular functions, they were two sides of the same cosmic coin. Modular functions, which string theory uses to model higher dimensional vibrations, were somehow encoded in the monster's DNA. It's as if the universe left a secret cipher in pure math, waiting for us to decipher its relevance to physics. Now fast forward to quantum gravity, where theorists struggle to reconcile general relativity's smooth spacetime with quantum mechanics' pixelated chaos. The monster might offer a clue. Some models suggest that spacetime at the tiniest scales could be built from structures that resonate with the monster's symmetry, like a cosmic crystal vibrating in 200,000 dimensions. Others propose that black hole entropy, which seems to count the number of quantum states on an event horizon, might relate to the monster's mind-bending number of configurations. After all, if a black hole's surface can holographically encode its interior, perhaps the monster's symmetry is the language of that encoding. Yet for all its promise, the monster remains enigmatic. We've mapped less than a fraction of its structure, and no physical system we know exhibits its full symmetry. But that's the thrill of the hunt, whether the monster is a mathematical curiosity or the skeleton key to quantum gravity. It reminds us that the universe's deepest symmetries might be hiding in plain sight, scribbled in the margins of equations we're only beginning to understand. What if time itself could crystallize not in a metaphorical sense, but as a real, physical structure that defies our most basic assumptions about how the universe flows? That's the bizarre promise of time crystals, a phase of matter so strange it was once thought impossible. Unlike ordinary crystals like diamonds or snowflakes where atoms arrange in repeating patterns in space, time crystals tick to a rhythm that repeats in time, creating a perpetual motion machine that doesn't violate the laws of physics. The idea began as a thought experiment. In 2012, Nobel laureate Frank Wilczek wondered, if regular crystals break spatial symmetry by locking atoms into grids, could something break time symmetry by oscillating without energy input? Skeptics argued this would defy thermodynamics. A system can't cycle forever without losing energy. But Wilczek's hunch was subtler. Time crystals don't create energy. They exist in a quantum ground state, meaning they're already at the lowest possible energy. Their secret: they exploit a loophole where periodic motion emerges not from energy, but from the quantum entanglement of particles conspiring to flip states in perfect sync, like a clock that ticks even when its batteries are dead. Proving this required quantum choreography. In 2017, two teams, one at Harvard, another at the University of Maryland, built the first time crystals using chains of ytterbium ions and nitrogen vacancy diamonds. They poked these systems with laser pulses not to add energy but to entangle particles into a stable rhythm. The result: the systems began flipping between states at periods longer than the laser's pulses, a fingerprint of time symmetry breaking. It's as if you tapped a pendulum every second, and it swung once every 2 seconds instead, marching to its own quantum drumbeat. The implications ripple far beyond labs. If time crystals are stable, they might serve as perfect quantum memory, storing data in their unshakable rhythms, immune to decoherence. But the real shocker is cosmological. Some theorists speculate that time crystals could have formed in the early universe's extreme conditions, freezing primordial quantum fluctuations into spacetime itself. Imagine vacuum fluctuations not as random noise, but as a crystalline lattice of events ticking across eons. This could reshape how we see time's arrow, not as an emergent property, but as a structural feature woven into reality's fabric. Yet mysteries linger. Can time crystals exist without external driving, truly isolated? Do they hint at deeper symmetries between time and space? For now, these questions hover at the edge of known physics, where the universe's most profound secrets often hide not in grand explosions, but in the quiet, persistent ticking of quantum clocks we're just learning to hear. Imagine the universe as a perfectly shuffled deck of cards. No matter how you look at it, the distribution of stars, galaxies, and radiation should be random and even. That's what cosmologists assumed about the cosmic microwave background, the afterglow of the Big Bang. But in 2003, astronomers studying data from NASA's Wilkinson microwave anisotropy probe stumbled onto something that sent chills down the scientific community's spine. The CMB wasn't perfectly uniform. Instead, its fluctuations seemed to align along a mysterious axis, as if the universe had a hidden equator, a line of symmetry we weren't supposed to notice. They called it the axis of evil. On one level, the name is just scientific dark humor, but beneath the joke lies a genuine unease. The CMB is our universe's baby picture, frozen in time just 380,000 years after the Big Bang. According to the standard cosmological model, its hot and cold spots should be sprinkled randomly like static on an old TV. Instead, researchers found these spots clustering in a way that traces an eerie line across the sky, a pattern so improbable that the odds of it happening by chance are less than 1 in 10,000. It's as if someone drew an arrow on the cosmic blueprint, pointing to a direction we can't explain. Skeptics have offered mundane explanations. Maybe it's an artifact of how we process the data, like a smudge on a camera lens distorting the image. Some suggest our solar system's motion through the CMB creates a Doppler effect that artificially stretches the pattern. Others argue that incomplete sky surveys or foreground interference from galactic dust could be painting a false signal. But even after accounting for these factors, the anomaly persists, gnawing at the edges of cosmology's most sacred principle, the cosmological isotropy, the idea that the universe looks the same in all directions. Then come the radical interpretations. Could the axis of evil be evidence of a pre-Big Bang structure, a fingerprint from a previous cosmic cycle? Roger Penrose's conformal cyclic cosmology suggests our universe might be one in an endless chain, with gravitational waves from colliding black holes in the previous eon imprinting concentric circles, or perhaps lines on the CMB. Others whisper about a cosmic defect, a crack in spacetime's fabric left over from the universe's violent birth, like a scar from a long-forgotten wound. And yes, there are even those who dare to mention the taboo word, design. Not necessarily a designer, but some fundamental constraint or boundary condition that shaped the early universe in ways we don't yet understand. The most unsettling possibility, that the axis is a window into something beyond our observable universe. Inflation theory says our cosmos is a tiny bubble in an infinite multiverse. If another bubble collided with ours during inflation, the impact could have left a bruise, a directionality etched into the CMB. It's like finding a dent in your car door and realizing it lines up perfectly with a lamppost you've never seen. For now, the axis of evil remains an enigma. Planck satellite data confirmed the anomaly but couldn't explain it. Future telescopes, like the proposed CMB S4 project, aim to map the CMB with even finer resolution, searching for clues in the polarization of ancient photons. Whether the axis crumbles under scrutiny or leads us to a new cosmological paradigm, one thing's clear: the universe might be more asymmetrical or symmetrically strange than we ever imagined. And that's a mystery worth chasing to the edge of the cosmos. Einstein's equations once described a static universe until Hubble discovered it was expanding. Today, we know that expansion is accelerating, and the cosmos seems to be stretching toward a future where galaxies vanish beyond an unreachable horizon. This eerie fate has a name: de Sitter space, a universe where dark energy dominates completely, and spacetime stretches so fast that even light can't keep up. But here's the twist. This seemingly bleak scenario might be hiding one of nature's most perfect symmetries, a cosmic balance so profound it could redefine our understanding of reality. De Sitter space isn't just any vacuum, it's a vacuum with a built-in symmetry so powerful that mathematically every point is identical. No center, no edge, no preferred direction. It's like standing in an infinite hall of mirrors where the reflections never distort, no matter how far you walk. This symmetry stems from dark energy's relentless push, which smooths out wrinkles in spacetime until the universe becomes featureless, cold, and eerily uniform. In a sense, de Sitter space is the ultimate triumph of symmetry over chaos, a cosmic blank slate where even time loses its arrow, ticking forward in a never-ending, unchanging present. Now compare this to its shadowy twin, anti-de Sitter space, or AD-S. Where de Sitter space expands, AD-S contracts, its negative curvature pulling spacetime inward like a cosmic trampoline. While de Sitter might describe our universe's far future, AD-S has become the darling of theoretical physics for a very different reason. It's the playground where holography comes to life. The AD-S/CFT correspondence, that radical idea linking gravity in bulk space to quantum theories on its boundary, relies entirely on AdS's neat, predictable geometry. It's a universe with walls where particles bouncing off the edges create echoes that encode everything happening inside. But here's the puzzle: our universe isn't AdS. It's accelerating toward de Sitter. So why does AdS get all the attention? Because de Sitter space is slippery. Its horizons hide information, its expansion scrambles signals, and its symmetries are harder to untangle. Yet clues suggest they might be even richer. Some theorists propose that de Sitter, like AdS, could have a holographic description not on a distant boundary, but on its cosmic horizons where fleeing galaxies vanish from view. Others speculate that de Sitter's symmetry might explain the unnerving smoothness of our universe, as if dark energy isn't just stretching space but ironing it into perfect mathematical uniformity. The stakes: if de Sitter's symmetry holds the key to quantum gravity in our real universe, it could unlock secrets about dark energy, the Big Bang, even the fate of time itself. Maybe the universe isn't just headed toward symmetry, maybe it's been yearning for it all along, a cosmic pendulum swinging toward perfect balance. And if that's true, then the endless expansion we dread might not be the end of the story, but the universe finally settling into its truest, most symmetrical form. In the heart of every magnet, there's an unbreakable rule: north and south poles always come in pairs. Snap a bar magnet in half, and you don't get isolated north or south poles. You get two new magnets, each with both poles intact. This symmetry is so fundamental we barely question it. But in 1931, physicist Paul Dirac dared to ask, what if single magnetic poles could exist? These hypothetical particles, dubbed magnetic monopoles, would rewrite the laws of electromagnetism and might hold the key to unifying all of nature's forces. Dirac's math revealed something astonishing. If even one magnetic monopole existed anywhere in the universe, it would explain why electric charge comes in fixed, discrete units, a mystery that had baffled scientists for decades. The logic was elegant. Just as electric charge creates a flux of electric field lines radiating outward, a magnetic charge would do the same for magnetic field lines. But unlike electric charges, which can stand alone, think electrons or protons, magnetic charges had never been found solo. Why? Dirac speculated they might be unimaginably rare, or perhaps hiding in places we hadn't thought to look. Fast forward to grand unified theories, or gut ambitious frameworks aiming to merge electromagnetism with the nuclear forces. These theories predict that in the searing heat of the early universe, symmetry breaking should have created magnetic monopoles as cosmic relics. Picture the universe cooling from a perfect, symmetrical state, like water freezing into ice. As it transitions, cracks form, and in this case, those cracks could be monopoles, frozen into existence with masses a quadrillion times heavier than a proton. If JUTs are right, the cosmos should be swimming with them. Yet here's the puzzle: despite decades of searching, not a single monopole has been definitively caught. Particle colliders have come up empty. Lunar rock and deep-sea sediment analyzers, which could trap monopoles like cosmic fossils, show no traces. Even the sprawling detectors designed to spot these elusive particles, like the Mo-Edel experiment at CERN, where monopoles might leave unique ionization trails, have yet to report a smoking gun. The absence is so glaring it's known as the monopole problem, and it's one reason inflation theory was proposed. Perhaps the universe expanded so rapidly after the Big Bang that monopoles were diluted to near zero density. But the hunt isn't over. Some theorists suspect monopoles might disguise themselves as transient quasi-particles in exotic materials like spin ices, where collective electron behavior mimics isolated magnetic charges. Others look to the cosmos, where ultra-high-energy cosmic rays might carry monopoles from distant galaxies. There's even a wild possibility that monopoles could catalyze proton decay, turning ordinary matter into energy, a signature that detectors like Supersymmetry and are primed to catch. The stakes couldn't be higher. Finding a monopole wouldn't just validate Dirac's vision. It'd be direct evidence for grand unification, proving that the forces we see as separate today were once one. It might even help explain why our universe seems fine-tuned for life, a fluke that could arise naturally from symmetry breaking on cosmic scales. Until then, monopoles remain both a tantalizing prediction and a stubborn ghost, hiding in the equations but not yet in our detectors. And that's the thrill of physics. Sometimes the universe's most elegant symmetries are the ones it fights hardest to keep secret. Picture a quantum particle like an electron until you measure it. It exists in a haze of possibilities, spinning both clockwise and counterclockwise simultaneously. Now imagine if every time someone looked at it, the universe had to decide which version of reality to show them. Shouldn't all those observers see something different? Yet somehow we all agree on whether the electron is up or down. This is the puzzle quantum Darwinism tries to solve. How does subjective quantum weirdness collapse into the objective world we all share? The answer might lie in a ruthless cosmic selection process. Think of it like evolution, but for quantum states. In a sea of infinite possibilities, only the most fit states survive. The ones that can imprint themselves onto the environment in countless redundant copies. Every photon bouncing off an object, every air molecule colliding with it, becomes a tiny observer, passively recording the same information. Over time, these imprints add up, creating a consensus reality so robust that no single observer can contradict it. It's like 1,000 photographers snapping pictures of the same event. While each photo might have tiny variations, the central subject remains unmistakably clear. Here's where symmetry breaking sneaks in. At the quantum level, all possible states are perfectly symmetrical, like a pencil balanced on its tip. But just as the pencil must eventually fall left or right, interactions with the environment break the symmetry, forcing the system to choose a state. The more this state gets copied into the air, the light, even the dust particles around it, the more it resists flipping back. Quantum Darwinism suggests that what we call reality is simply the subset of quantum states that have outcompeted their alternatives by spreading their information far and wide. This isn't just philosophy. Experiments with quantum dots and entangled photons have shown how certain states rapidly proliferate while others fade, as if the universe itself is conducting a survival of the fittest tournament for facts. Even your brain relies on this principle. The reason you see a chair as solid rather than a probability cloud is that trillions of interactions have broadcast its position and shape into the environment so thoroughly that your senses can't help but agree. But quantum Darwinism goes further. It hints that the symmetries we perceive, like the arrow of time or the uniformity of space, might emerge from this same copying process. Just as natural selection explains why life converges on efficient designs, quantum selection could explain why reality converges on stable, shared experiences. The universe isn't just symmetric or broken, it's constantly holding elections, and the winners become the world we all inhabit. So next time you glance at a tree or touch a table, remember, you're not just observing reality. You're joining a chorus of trillions of observers, past and present, all reinforcing the same answer to the universe's most persistent question: what happens next? And in that chorus, symmetry doesn't vanish, it evolves. It's one of the most haunting questions in science. Why does math work so well at describing the universe? From the spirals of galaxies to the orbits of electrons, the world seems to obey mathematical rules with eerie precision. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences, a phrase that captures both the wonder and the unease of this discovery. It's as if the universe isn't just described by math, it's made of it. But is this profound symmetry a clue to the cosmos's deepest truths? Or are we just seeing patterns because those are the only ones we know how to look for? Take Newton's law of gravity. When he wrote down the equation for the gravitational force between two objects, it wasn't just a rough approximation, it predicted planetary motions with uncanny accuracy, even centuries before we could send probes to test it. Or consider Maxwell's equations, which unified electricity and magnetism in the 1800s. They didn't just explain known phenomena, they predicted radio waves, a discovery that reshaped human civilization. And then there's quantum mechanics, where the math, bizarre as it is, has been verified to something like 12 decimal places. It's not just that math fits reality, it often outruns it, revealing truths about nature we hadn't even thought to question. So why does this work? One camp argues that math is discovered, not invented, that equations like E equals mc squared or the Schrödinger wave function are as real as mountains or stars, waiting for us to uncover them. In this view, the symmetries we find in math, from the simplicity of pi to the elegance of group theory, aren't human constructs. They're the scaffolding of reality itself, written in a language we're only beginning to decode. The fact that imaginary numbers, once dismissed as useless abstractions, turned out to be essential for describing quantum fields only deepens the mystery. But skeptics push back. Maybe math works because it's the only tool we have that can work. Imagine a fish trying to describe water. It has no concept of wetness because it's never known anything else. Similarly, we're embedded in a universe where only certain phenomena are observable, and only certain kinds of math can model them. We celebrate the successes and ignore the failures, a form of selection bias that makes math seem more universal than it is. After all, for every Newton or Einstein, there are countless dead-end theories with beautiful math that just didn't pan out. Then there's the pragmatic middle ground. Math isn't inherently magical, but it's the ultimate optimization tool. Evolution wired our brains to recognize patterns, and math is pattern recognition refined to its purest form. When we find symmetries in nature, we're not uncovering cosmic blueprints, we're inventing lenses that bring the world into focus. The miracle isn't that math describes the universe, it's that our brains evolved to invent math capable of describing it. Yet the debate rages on. Some theorists suggest that if we ever encounter alien civilizations, their math might look nothing like ours. Their numbers could be tied to entirely different symmetries or dimensions. Others argue that advanced physics will always converge on the same underlying structures, no matter who's doing the calculating. For now, the mystery remains unsolved, suspended between two equally breathtaking possibilities: that we're either glimpsing the universe's secret language or staring into a mirror of our own making. Either way, the symmetry between math and nature isn't just a tool, it's a riddle written into the fabric of existence, daring us to look deeper. Imagine throwing a book into a fire. The pages burn, the ink fades, but in principle, if you could track every wisp of smoke and every vibration in the ashes, you could reconstruct the original text. That's how physics has always worked. Information might get scrambled, but it's never truly lost. Then along came black holes, and suddenly the rules seemed to break. When Stephen Hawking showed these cosmic monsters could evaporate over eons, leaking radiation so random it erased all traces of what fell in, the universe's playbook seemed to tear in half. If black holes could delete information, then time reversal symmetry, the sacred rule that physics runs just as well backward as forward, was nothing but an illusion. The stakes were enormous: lose unitarity, the principle that quantum information must be preserved, and the foundation of quantum mechanics crumbles. For decades, physicists wrestled with this paradox, splitting into warring camps. Some, like Hawking himself, initially bet information was truly gone, a heresy that would have rewritten reality. Others clung to faith that the universe wouldn't allow such cosmic censorship. The breakthrough came from an unexpected direction: the holographic principle. If black holes encode everything they swallow on their event horizons like a celestial hard drive, then maybe the information isn't lost, just locked in a code we couldn't crack. Enter the island conjecture, a daring idea that reshapes how we see black hole interiors. Picture the event horizon not as a one-way curtain, but as a quantum firewall where information gets duplicated. One copy escapes as Hawking radiation, while another stays etched on the surface. The trick is that these copies aren't independent. They're entangled, connected by invisible threads through spacetime's quantum foam. The island refers to a hidden region inside the black hole that somehow remains entangled with the outgoing radiation, acting as a bridge to preserve the original data. It's as if the universe, faced with a paradox, grew extra dimensions just to balance its books. This isn't just theoretical sleight of hand. Recent calculations show the island conjecture perfectly restores unitarity, matching predictions from quantum gravity frameworks like ADS/CFT. Even Hawking, in his final paper, conceded the information probably escapes, though how remains hotly debated. Some models suggest the interior of a black hole isn't a void but a chaotic quantum computer, performing the ultimate encryption. Others speculate that wormholes stitch the island to the exterior, turning Einstein's spooky action at a distance into a literal lifeline for information. The most mind-bending implication, time symmetry might not be broken after all, just stretched across scales we're only beginning to map. When a black hole evaporates, the information doesn't vanish. It undergoes a cosmic metamorphosis, scrambled into a form so alien we mistook it for noise. The island conjecture hints that beneath the paradox lies a deeper symmetry, one where even the fiercest gravitational prisons can't silence the universe's stubborn habit of remembering. And if that's true, then black holes aren't cosmic shredders, they're the ultimate archivists, keeping secrets in a language we're just learning to read. Empty space isn't really empty. Quantum physics tells us it's a seething, bubbling foam where particle-antiparticle pairs constantly blink in and out of existence. These fleeting fluctuations give the vacuum an inherent energy, what physicists call vacuum energy or zero-point energy. According to quantum field theory, this energy should be enormous, with every cubic centimeter of space crackling with enough power to rip atoms apart. But when we look out at the universe, we see the opposite. Space isn't violently unstable. It's eerily calm, expanding at a gentle, accelerating pace driven by dark energy. The problem, the predicted vacuum energy is 10 to the 120th power times larger than what we observe. That's a 1 followed by 120 zeros, a number so absurdly big it makes the difference between the size of a proton and the observable universe seem trivial by comparison. This mismatch isn't just a minor accounting error, it's the single worst prediction in the history of physics. Imagine calculating how much water should be in your bathtub and getting an answer equivalent to all the oceans on Earth. That's the scale of our cosmological constant problem, and it's been baffling theorists since Einstein first introduced the constant in his equations. The kicker, the universe doesn't just have slightly less vacuum energy than expected. It's almost perfectly balanced at near zero, as if some unseen hand carefully dialed it to precisely the tiny value that allows galaxies, stars, and life to exist. Why does this break symmetry? Because quantum mechanics and general relativity should meet seamlessly in their description of empty space. Instead, they violently disagree. Quantum theory suggests spacetime should be bent into pretzels by vacuum fluctuations, while cosmology shows us a smooth, nearly flat universe where dark energy's effect is almost imperceptibly small. It's as if the laws of the very big and the very small are speaking entirely different languages with no common ground in between. Potential solutions range from the elegant to the bizarre. Some theorists propose supersymmetry could cancel out most of the quantum noise, leaving just a tiny residual energy we observe as dark energy. Others suggest an anthropic principle at work. Maybe countless universes exist with randomly varying vacuum energies, and we're here simply because ours happen to land in the habitable sweet spot. Then there are wilder ideas like vacuum energy being an emergent property rather than a fundamental one, or the possibility that we're misinterpreting dark energy entirely, that cosmic acceleration comes from some undiscovered fifth force or a flaw in Einstein's gravity theory. Perhaps the most radical notion is that the cosmological constant isn't constant at all. Maybe it decayed from an initially huge value to nearly zero during the universe's first fractions of a second, freezing at its current feeble strength. This would mirror how other fundamental forces froze out during cosmic symmetry breaking, like when the electromagnetic and weak nuclear forces split apart as the universe cooled. If true, the vacuum energy we measure today might be just the leftover dregs of a much grander symmetry from the dawn of time, one that's since hidden itself in plain sight. As it stands, the cosmological constant problem remains a glaring hole in our understanding, exposing how little we grasp about the interplay between quantum mechanics and gravity. It's a humbling reminder that for all our equations and discoveries, the universe still holds symmetries so profound we've barely begun to glimpse their edges, let alone understand why they appear so delicately, miraculously broken. At first glance, neutrinos seem like nature's most indifferent particles, ghostly, nearly massless, and so reluctant to interact that trillions pass through your body every second without a trace. Yet these cosmic specters hold a stunning secret. They're shape-shifters. A neutrino born in the heart of the sun might start its journey as an electron neutrino, only to morph into a muon or tau neutrino before reaching Earth. This bizarre phenomenon, called neutrino oscillation, isn't just a curiosity, it's proof that even nature's most fundamental symmetries aren't as perfect as we once thought. The shock came in the late 1990s when experiments like Supersymmetry discovered that neutrinos produced in the atmosphere were vanishing en route to detectors. They weren't disappearing, they were changing identities mid-flight, like actors swapping costumes in the dark. The math revealed why. Neutrinos have mass, albeit vanishingly small, and their mass states don't align with their flavor states electron, muon, or tau. Instead, they exist as quantum superpositions, oscillating between flavors as they travel. This shattered the long-held assumption that neutrinos were massless, as predicted by the Standard Model's pristine symmetries. But the real bombshell was what this implied about the weak nuclear force, the fundamental interaction governing neutrino behavior. For decades, physicists assumed this force treated particles and antiparticles with perfect symmetry, a principle called CP conservation. Yet neutrino oscillations hinted otherwise. If neutrinos and antineutrinos oscillate at slightly different rates, it would mean the weak force subtly favors matter over antimatter. Imagine a coin that, when flipped, lands heads just a fraction more often than tails. Over billions of flips, or in this case, particle interactions, that tiny bias could snowball into the overwhelming matter dominance we see today. This cosmic sleight of hand might explain one of the universe's greatest mysteries, why there's something rather than nothing. During the Big Bang, matter and antimatter should have annihilated each other completely. The fact that we exist means something. Some asymmetry tipped the scales. Neutrino oscillations offer a tantalizing clue. Experiments like T2K in Japan and NAVA in the US have been racing to measure the difference in oscillation rates between neutrinos and antineutrinos. Early data suggests a discrepancy, though not yet conclusive. If confirmed, it would mean neutrinos aren't just breaking symmetry, they're the architects of our material universe. The stakes are cosmic. If neutrinos violate CP symmetry enough, they could have triggered a process called leptogenesis in the early universe. Here's how it might work. Ultra-heavy neutrinos from the Big Bang decayed asymmetrically, producing more matter than antimatter. Through quantum alchemy, that imbalance then cascaded into the quark sector, seeding the matter surplus that built galaxies, stars, and us. It's a chain reaction starting with the tiniest particles and ending with everything we see. Yet mysteries linger. why are neutrinos so absurdly light compared to other particles? Their masses are at least 1,000,000 times smaller than the electrons, a hierarchy that defies explanation. Some theories propose they're majorana particles, meaning they're their own antiparticles. This would imply that neutrinos are essentially cosmic doppelgangers, with their matter and antimatter versions identical. Experiments like the proposed neutrinoless double beta decay searches aim to test this wild idea. If true, it would rewrite our understanding of particle physics and potentially reveal why the universe treats matter and antimatter so unfairly. For now, neutrinos remain both messengers and riddles, tiny, elusive, and freighted with the weight of cosmic imbalance. Every time one oscillates, it's not just changing flavor, it's whispering secrets about the broken symmetries that made our existence possible. And as detectors grow more sensitive, we might soon hear those whispers clearly for the first time, decoding how the universe tilted the scales in favor of stuff and, by extension, us. What if our universe's laws of physics aren't the only possible configuration, just the winning ticket in a cosmic lottery with 10 to the 500 possible outcomes? This is the jaw-dropping implication of inflationary multiverse theory, where the symmetry-breaking events that shaped our reality might be just one flicker in a firestorm of universes, each with its own unique rules. The idea starts with inflation, that brief instant after the Big Bang when space-time expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. But here's the twist. According to theorists like Andre Lind, inflation might never have stopped everywhere. Instead, it could be eternal, with bubbles of stability. Entire universes like ours nucleating like droplets in a boiling sea of hyper-expanding spacetime. Inside each bubble, random quantum fluctuations trigger symmetry breaking, freezing out different fundamental forces and particles. Picture a vast landscape of possible vacuous stable configurations of spacetime's energy, where every valley represents a unique set of physical constants. String theory takes this further, suggesting there could be 10 to the 500 such valleys in the string theory landscape, each corresponding to a universe with different particle masses, forces, even dimensions. In this view, our universe's delicate balance, where gravity is weak enough to allow galaxy formation but strong enough to hold planets together, isn't designed. It's just the roll of the dice that produced a habitable universe, with countless others doomed to barren emptiness or instant collapse. The eerie elegance of this idea is how it reframes the anthropic principle. Instead of asking why our universe seems fine-tuned for life, we might be asking the wrong question altogether. If every possible physics plays out somewhere, then of course we find ourselves in a universe that permits our existence. The alternatives simply don't have observers to wonder about it. Even the cosmological constant problem, where vacuum energy is inexplicably tiny, could be a selection effect. In most universes, dark energy is too strong, ripping atoms apart before life can form. Only in rare bubbles like ours does it land in the Goldilocks zone. Critics argue this smacks of surrender, replacing testable physics with an infinite, anything-goes multiverse. But there are potential fingerprints. If our bubble universe collided with another during inflation, the crash could have left scars in the cosmic microwave background, like the controversial cold spot detected by Planck. Others suggest that the detailed pattern of primordial gravitational waves, if ever measured, might reveal whether inflation truly is eternal. And then there's string theory's gamble. If we could somehow prove that the theory's landscape of vacua is real, even indirectly, it would lend weight to the multiverse as more than metaphysical speculation. What's profound here isn't just the scale, it's how radically this reshapes our notion of symmetry. The forces we see as immutable might be frozen accidents, shards of a higher dimensional symmetry shattered across creation. The Higgs field's value, the strength of gravity, even the number of dimensions could all be local quirks in a tapestry of universes where symmetry breaks differently every time. It's as if we've spent centuries studying a single ice crystal, only to realize it's one facet of a snowflake vaster than the cosmos itself, and that every possible crystal pattern exists somewhere in the storm. When we look up at the night sky, we assume space stretches endlessly in every direction, a vast, featureless expanse. But what if the universe isn't infinite at all? What if it's folded into an intricate shape so enormous that its curvature eludes our telescopes, hiding symmetries as precise as a gemstone's facets? This is the wild frontier of cosmic topology, where mathematicians and physicists hunt for the universe's true geometry by studying the faintest echoes of the Big Bang. One leading candidate is the Poincaré dodecahedral space, a mind-bending structure where the cosmos wraps around itself like a holographic soccer ball. Named after the mathematician Henri Poincaré, this model imagines space tiled with 12 identical pentagon-shaped regions. Travel far enough in any direction, and you'd loop back to your starting point, not because space bends, but because it's stitched together in a higher dimensional knot. The symmetry here is staggering. No matter where you stand, the universe looks the same in all directions, yet it's finite, with no edges or center. It's like living on the surface of a planet, but with an extra layer of complexity woven into the fabric of space-time itself. How could we ever detect such a shape? The answer lies in the cosmic microwave background, the afterglow of the Big Bang. If the universe is a dodecahedron, light from the early cosmos would have taken multiple paths to reach us, creating telltale repeating patterns in the CMB's temperature fluctuations, like a hall of mirrors reflecting the same image at different angles. In 2003, a team analyzing data from NASA WMAP satellite thought they'd spotted these very echoes, matching circles in the sky where temperatures aligned with eerie precision. Though later studies cast doubt, the possibility remains tantalizing. Imagine the universe not as a formless void, but as a cosmic cathedral, its walls adorned with symmetries left over from creation. Then there's cosmic crystallography, a method that treats the universe like a crystal lattice. Just as X-rays reveal a crystal structure by how they diffract, astronomers could map space-time's hidden geometry by studying how galaxies cluster at vast scales. If the cosmos repeats like a kaleidoscope, we'd see identical arrangements of galaxy clusters separated by specific distances, ghostly fingerprints of a folded universe. Projects like the Sloan Digital Sky Survey have scoured billions of galaxies for these patterns, but so far, the data remains inconclusive. The challenge is akin to trying to discern the shape of a room by studying the reflections in a single, foggy mirror. Critics argue these models are beautiful but unnecessary, that Occam's razor favors a simple, infinite universe, yet the quest persists because the stakes are cosmic. A finite, symmetrical universe would answer one of cosmology's oldest questions: what lies beyond the observable horizon? In a dodecahedral space, there is no beyond. The universe just folds back on itself, a cosmic Möbius strip where every path leads home. It would also explain why the CMB's large-scale fluctuations seem oddly subdued, as if the universe, like a finely tuned instrument, can't vibrate beyond certain harmonious frequencies. Whether the cosmos is a shimmering dodecahedron or an infinite plane, the search for its shape reveals a deeper truth. Symmetry isn't just a property of particles or forces. It might be etched into the very architecture of spacetime, waiting for us to decipher its grand design. And if we one day crack the code, we won't just understand the universe's structure, we'll glimpse the blueprint of reality itself. At scales smaller than the Planck length, roughly a trillionth of a trillionth of a trillionth of a meter, our everyday notions of space and time begin to shatter like glass under a hammer. This is the frontier where quantum gravity theories dare to tread, proposing that space-time itself might not be smooth and continuous, but pixelated, like a cosmic mosaic frozen in place. Imagine zooming in on a digital photo until you see the individual pixels. At the Planck scale, reality might reveal a similar graininess, a fundamental limit beyond which here and there lose all meaning. Loop quantum gravity takes this idea and runs with it, painting spacetime as a web of interconnected loops, each carrying tiny quanta of area and volume. Picture a vast dynamic tapestry where the threads aren't woven from fabric, but from gravitational fields themselves. These loops don't exist in space, they are space, merging and splitting in a dance that generates the geometry we experience. When matter moves through this network, it's not traversing a passive backdrop, it's tugging on the threads, reshaping the very stage it walks across. The symmetry of classical spacetime, where every point is equivalent and directions are interchangeable, breaks down here, replaced by a quantum foam where distances and durations fluctuate wildly. Causal set theory approaches the problem from a different angle, stripping reality down to its most minimalist essence, a collection of discrete events linked by cause and effect. Think of it as the universe's version of a family tree, where each event is a node and the connections between them dictate the flow of time. There's no smooth continuum, just a sprawling, branching structure where before and after are the only meaningful coordinates. In this view, the illusion of smooth spacetime emerges from the collective behavior of countless events, much like the illusion of a flowing river arises from the motion of individual water molecules. The symmetry of times arrow the idea that physics works the same way forward and backward gets rewritten at this level, with causality itself serving as the universe's primal building code. Both theories converge on a startling implication. The Planck scale isn't just another rung on the ladder of smallness, it's a wall, a point where the very concept of smaller ceases to exist. Attempts to probe shorter distances would require so much energy that they'd collapse into black holes, as if the universe were enforcing a speed limit on curiosity. This radical finiteness challenges our intuitions about symmetry at every turn. Why should space and time, which seem so fluid and boundless, suddenly hit a hard stop? Some speculate it's nature's way of preventing infinities from plaguing quantum gravity equations, a cosmic censorship that keeps the fabric of reality from tearing at the seams. Yet the most tantalizing clue lies in the black hole entropy calculations of physicists like Jacob Bekenstein and Stephen Hawking. When they found that a black hole's entropy, its hidden information, is proportional to the area of its event horizon, not its volume, it hinted at spacetime's fundamentally pixelated nature. If loop quantum gravity or causal sets are correct, those pixels might be the ultimate resolution of reality, the smallest possible stitches in the quilt of existence. And if we ever learn to read their patterns, we might finally understand how the universe stitches together quantum weirdness and gravitational order into a single, seamless whole. For now, these ideas remain just beyond our grasp, like shadows flickering at the edge of a Planck scale candle. But they remind us that symmetry, for all its beauty, might not be the universe's deepest language. Beyond a certain threshold, the rules change, and the cosmos reveals itself not as a perfect continuum, but as a dynamic, quantum-grained masterpiece, one pixel at a time. Black holes are cosmic monsters, devouring everything that strays too close, even light itself. Electrons, on the other hand, are the quiet workhorses of the quantum world, buzzing around atoms so small they barely seem to exist at all. But what if these two extremes, the infinitely dense and the infinitesimally tiny, were secretly the same thing? That's the jaw-dropping premise of the black hole electron hypothesis, a theory so bold it erases the line between particle physics and general relativity. Think of an electron's properties, its charge, its spin, its stubborn refusal to occupy the same quantum state as another electron. Now imagine compressing all that into a volume so small it collapses into a black hole. The math reveals something startling. A black hole with the electron's mass would have a Schwarzschild radius of about 10 to the negative 57 meters, absurdly smaller than the Planck length. Yet if you plug in quantum corrections or extra dimensions from string theory, the numbers start to align. Suddenly, the electron's charge could be interpreted as the hair of a microscopic black hole, and its spin might reflect the rotation of an event horizon too tiny to see. This isn't just numerology. If electrons are black holes, it could explain some of quantum mechanics' weirdest quirks. Take wave-particle duality, the fact that electrons act like both particles and waves. A black hole electron might naturally exhibit this behavior, with its event horizon smearing its position into a probability cloud. Even entanglement gets a geometric twist. Two black hole electrons could link through microscopic wormholes, their horizons entangled like cosmic twins. It's as if quantum weirdness isn't a bug, it's a feature of spacetime's deepest structure. But how could something so dense not swallow the universe? Here's where the theory gets clever. In some models, these mini black holes are extremal, meaning their electric charge perfectly balances their gravitational pull, preventing runaway collapse. Picture a black hole hovering on the edge of existence, its repulsive charge pushing outward just enough to counter the inward crush of gravity. This delicate equilibrium might be why electrons are stable, lasting billions of years without decaying or exploding. Of course, skeptics pounce on the elephant in the room. Where's the Hawking radiation? Traditional black holes evaporate over time, but electrons don't. Proponents argue that quantum effects or extra dimensions could suppress radiation, effectively freezing the black hole in place. Others suggest electrons aren't solitary black holes but fuzzballs, string theory objects with no sharp horizon, blurring the line between particle and spacetime defect. The implications ripple far beyond tidy equations. If electrons are black holes, then every atom in your body is built from constellations of microscopic singularities. Chemistry becomes applied general relativity, and the vacuum of space might seethe with hidden event horizons. Most tantalizingly, this could be the missing link between quantum mechanics and gravity, a bridge built not from abstract math, but from the idea that the universe's smallest pieces are also its most extreme. For now, the black hole electron remains a provocative thought experiment, lacking smoking gun evidence. But it reminds us that sometimes the most radical symmetries hide in plain sight, waiting for us to question assumptions we never knew we'd made. After all, if a black hole can wear the mask of an electron, what other cosmic disguises might we have overlooked? What if time isn't a river flowing inexorably forward, but an illusion? A trick of perspective hiding a universe where every moment exists eternally in a vast, frozen landscape of possibilities. This is the radical vision of physicist Julian Barbour, who argues that time doesn't exist at all. Instead, what we perceive as past, present, and future might be nothing more than isolated snapshots in an infinite gallery of nows, arranged by a hidden symmetry so profound it rewrites the rules of reality. Barbour's theory starts with a simple but staggering idea. The universe is a collection of all possible configurations, every arrangement of particles, every twist of spacetime existing simultaneously in a timeless pluriverse he calls Platonia. In this view, what we experience as the passage of time is just our consciousness hopping from one configuration to another, like a moviegoer mistaking the rapid succession of still frames for motion. The key lies in the symmetry between these configurations. Some arrangements are so perfectly balanced that they act as anchors, creating the illusion of sequence. Imagine a deck of cards shuffled into every possible order. Most sequences look random, but a rare few, like a perfectly ordered ace to king run, stand out as special. These are the universe's Janus points, moments of maximal symmetry where time seems to branch in two directions. Here's where it gets cosmic. Barbour proposes that the Big Bang wasn't the beginning. It was a Janus point, a moment of perfect symmetry from which our universe fractured into what we now call past and future. Picture an hourglass with two bulbs, one representing expansion, our universe evolving from the Big Bang, the other contraction, a mirror universe where entropy runs backward. Both flow away from the Janus point like reflections, neither more real than the other. What we perceive as the arrow of time is just our perspective from one side of the symmetry, like a hiker on a mountain ridge seeing only the valley below, unaware of the identical slope behind them. This isn't just philosophical wordplay. Barber's math suggests that gravity itself could emerge from the differences between these configurations. In a timeless universe, the force we call gravity might simply be the tendency for certain configurations to cluster around Janus points, creating the illusion of attraction. Even quantum mechanics gets a fresh interpretation. The famous collapse of the wave function might be our consciousness latching onto one path in Platonia's labyrinth while ignoring the rest. Skeptics, of course, demand evidence. How do you test a theory that erases time? Ironically, the clues might lie in the very fabric of time we're trying to explain. If the universe has a Janus point, its fingerprint could linger in the cosmic microwave background, a subtle statistical symmetry in the distribution of galaxies or the faint echo of a mirror universe's Big Bang. Others propose that black holes, those cosmic scrapbooks of information, might encode timeless physics in their event horizons where space and time twist into irrelevance. Whether Barber's vision holds or not, it forces us to confront a breathtaking possibility. That time, for all its visceral reality, might be the universe's most persuasive illusion, a shadow cast by symmetries too vast for us to see in full. And if that's true, then every tick of the clock isn't marking the passage of moments, but the turning of a cosmic kaleidoscope, revealing patterns that were there all along. What if the universe isn't the ultimate reality, just an unfathomably advanced simulation running on some cosmic computer? This isn't science fiction anymore. It's the simulation argument, a serious hypothesis that suggests our entire existence might be built on layers of computational symmetry. Think of how video games render only what the player sees to save processing power. Now imagine the universe doing the same, smoothing out details at quantum scales until observation forces it to render reality in higher resolution. At the heart of this idea is the pixelated universe hypothesis. Just as digital images break down into pixels when you zoom in far enough, space-time itself might have a fundamental resolution limit, a Planck scale, pixel size, where the smooth continuum of relativity gives way to discrete bits of information. The kicker: this isn't pure speculation. Some quantum gravity models already treat spacetime as a network of interconnected nodes, much like a cosmic graphics card processing reality frame by frame. Even stranger, certain interpretations of quantum mechanics like wave function collapse start to make eerie sense if you view measurement as the simulation, updating its state to conserve resources. But how could we ever test such a mind-bending claim? Surprisingly, there are experimental avenues. If the universe is pixelated, ultra-high-energy cosmic rays might behave differently when they approach the theoretical resolution limit, like pixels glitching in an overstretched video. Some physicists have proposed searching for anomalies in gamma-ray bursts that could reveal the simulation's underlying lattice structure. Others suggest quantum randomness might not be truly random. Hidden patterns could emerge in the digits of fundamental constants, like finding the signature of a programmer's algorithm in the decimals of pi. Then there's the symmetry angle. All simulations rely on optimization, reusing code, recycling assets, minimizing redundancy. If our universe is simulated, we might find identical mathematical templates repeating across vastly different scales, from the spirals of galaxies to the orbits of electrons. It would explain why so many physical laws exhibit fractal-like symmetry, as if the simulation is running on efficient, recursive algorithms. Even the holographic principle fits this view. A 3D universe rendered from 2D information sounds suspiciously like a cosmic rendering trick. Of course, skeptics abound. Some argue the simulation hypothesis is unfalsifiable, a modern-day brain in a vat with no clear exit. Others point out that simulating every particle in the universe would require more energy than the universe contains, making the whole idea paradoxical. But proponents counter that advanced civilizations might use techniques we can't fathom, like quantum computations or nested simulations within simulations, where each layer inherits simplified physics from the one above it. Whether you buy the argument or not, it forces a profound shift in perspective. If symmetry isn't just a property of nature but a feature of some deeper computational architecture, then the search for universal laws becomes something even stranger, a quest to reverse engineer the code of existence itself. And that changes everything from how we view consciousness to whether we might one day meet our simulators, or worse, discover we're the only ones left playing the game. Could the very act of observation be what gives the universe its structure? This isn't just a philosophical musing, it's a radical interpretation of quantum mechanics where consciousness isn't merely along for the ride, but actively weaving the fabric of reality. Consider the double-slit experiment, that cornerstone of quantum weirdness. When unobserved, particles behave like waves, creating interference patterns. But the moment you set up a detector to see which slit they pass through, they snap into definite positions like soldiers caught in a spotlight. It's as if reality changes its behavior based on whether anyone's watching. Now take this further. If observation collapses quantum possibilities into definite outcomes, could conscious observers, from humans to hypothetical alien intelligences, be the symmetry enforcers of reality? Some theorists propose that without observation, the universe remains a blur of probabilities, like an endless deck of cards where every possible hand is still in play. Consciousness, in this view, acts as a filter, selecting certain symmetrical patterns to crystallize into the stable world we experience. Think of how snowflakes form. Water molecules arrange themselves into intricate six-fold patterns, not because of some central blueprint, but because of local interactions constrained by deeper physical laws. Similarly, consciousness might be the local freezing point where quantum potentials condense into the symmetries we recognize as time, space, and physical laws. The anthropic principle, the idea that the universe's constants seem fine-tuned for life, gets turned on its head here. Instead of life emerging in a hospitable universe, conscious observation could be what sculpts the universe's hospitable symmetries in the first place. Critics argue this veers into mysticism, pointing out that observation in quantum mechanics just means interaction with any measuring device, not necessarily a conscious mind. Yet the line blurs when you consider that all measurements ultimately feed into conscious experience. Even the famous Schrödinger's cat thought experiment hinges on the moment a conscious observer opens the box, collapsing the superposition of live and dead states. The most extreme version of this idea comes from physicist John Wheeler, who envisioned a participatory universe where observers in the far future retroactively determine quantum outcomes at the Big Bang through the cosmic web of cause and effect. It's like the universe is a grand cosmic puzzle that only makes sense when viewed from the endpoint, with consciousness tracing the lines of symmetry backward through time. Whether this holds scientific weight or not, it forces us to confront a staggering possibility that the symmetries we take as fundamental might not be written into the universe's fabric, but drawn out by the very act of perception. And if that's true, then every time you open your eyes, you're not just seeing reality, you're helping to create it. From the fractal dance of galaxies to the quantum whispers of entangled particles, the universe reveals itself not as a haphazard chaos, but as a symphony of hidden symmetries. These 30 theories, each a thread in the cosmic tapestry, show us reality's obsession with balance, from the perfect curves of Calobi-Yau manifolds to the mirrored echoes of CPT invariants. Whether it's the holographic principle encoding 3D existence on 2D surfaces, or the monster group's gargantuan symmetry lurking in the equations of string theory, the message is clear. Beneath the surface of what we see, the cosmos is humming with order. But here's the thrilling part. Every time we peel back one layer of symmetry, another mystery shimmers into view. The universe seems to tease us with glimpses of a grander pattern, one that might unite quantum foam and galactic superclusters under a single, elegant rule. Could there be a master symmetry, a final equation that stitches every force, every particle, every dimension into a seamless whole? Or is the truth even stranger, that symmetry itself is just one note in a deeper, wilder harmony we've yet to imagine? As you look up at the stars tonight, consider this. Which of these theories resonates with you? Is it the cyclical rebirth of conformal cosmology, the geometric poetry of E8, or the holographic mirage of our 3D world? The conversation doesn't end here. The universe's greatest symmetries might still be waiting, not in some distant galaxy, but in the equations we've yet to write, the experiments we've yet to run. So tell us in the comments which hidden symmetry makes you pause, wonder, and see the cosmos anew. After all, the next revelation could start with